All right, today we're going to continue talking about sound waves and how different sound waves interact. Today, what I want you to figure out is what produces an echo, what causes a sonic boom, and how do musical instruments amplify sound? So, how do they make the sound louder? Um, so, the first part we're going to take a look at today is what happens when sound waves reflect. Okay, when sound waves reflect, that's called an echo. Okay, imagine shouting your name in an empty basketball court. A second later, you hear an echo of your voice come back to you. An echo is a reflected sound wave. Okay, it's reflected, it's coming back just like a light wave, but it's a little bit different because remember, there are longitudinal waves and light waves, a transverse wave, but the reflection happens when the wave bounces off a barrier. The loudness of a reflected sound wave depends on the properties of the surface the wave bounces off of. Sound waves reflect best off smooth, hard surfaces. So if you go look at like the lunchroom in the middle school, or sometimes if you see like soundproofing, they have that foam with those little bumps on there. And the reason why they have those bumps on there is because that makes it so the sound doesn't reflect. So like sometimes in gyms, they'll put these acoustic panels up on the gym so it doesn't echo as much. It's not as loud in there. Sound waves reflect off smooth, hard surfaces. So rough, uneven surfaces do not reflect sound waves very well. Therefore, these kinds of surfaces are used in auditoriums and classrooms to prevent echoes. So if you look at your reading check number 1, it says, what happens to an echo? Well, an echo is a reflected sound wave. And the more smooth and hard the surface is, the more it will echo. That's why we want to put like curtains and acoustic panels and things up so that echoes don't come back and forth, so you get a better acoustics in there. Echolocation. Many animals use echolocation to find food and to see objects that are in their way. Echolocation is used to reflect sound waves to find objects. Animals that use echolocations are bats, dolphins, and some birds. Now remember we talked about in our last lesson how sound waves travel through different mediums at different speeds. If you take a look at like a dolphin will use echolocation, but it'll travel a lot faster in water because water is a different medium and sound waves travel faster through water. What is echolocation? Echolocation is the use of reflected sound waves to find objects. Okay, reflected sound waves to find objects. Now, during echolocation, the animal produces a sound wave, and the sound bounces off the objects and returns to the animal's ears. Sound waves take longer to return from far away from objects than the near ones. So if I had like this camera here and I were to say something, it would take longer for the sound wave to hit the computer, and this one would come back quicker so then I can know that something was there. We all know that bats do that, so they can see things. They can see where things are. Echolocation technology, sonar, okay, we use that on boats and things, which stands for sound, navigation, and ranging, is a type of echolocation. People use sonar to find things underwater. Sonar usually uses ultrasonic sound waves. Their short wavelengths gives us more detail about the objects they reflect off of. Ships use sonar to locate and avoid icebergs and rocks. Scientists use sonar to map the ocean floor. People also use sonar to locate fish. I know the fishing opener is coming up. It may actually be next weekend, I think. A lot of you, if you go fishing, you have a fish finder, or you could see the depths. You can see the bottom of the lake, and that's what we use our fish finders and things like that, and our depth finders. We use sonar for that. So it kicks out a sound, and these wavelengths go back and they come back. Ultrasonography. Doctors can use a type of echolocation to see inside a person's body. In ultrasonography, ultrasonic waves reflect off patients' internal organs. A computer interprets the reflected waves as the image of the organs. Doctors use ultrasonography to look for damage to organs and to check the development of unborn babies. So sonographs and things like that. You'll go in if you're having a new baby, you'll go in and you'll be able to see those things, those ultrasounds. So that's what they call an ultrasound. So, all right, we're going to continue here in just a second. The next piece we're going to talk about is interference. We talked about this with waves. We talked about the two types of interference: constructive interference and destructive interference. Remember, constructive interference combines to make the wave bigger, and destructive interference combines to make the wave smaller. So constructive is when two crests meet and makes a bigger amplitude, and destructive interference is when we have a crest and a trough meet, so it's just like it levels it out. So interference happens when two or more waves overlap or combine. There are two types of interference: constructive and deconstructive interference. Constructive interference happens when compressions from one wave combine with compressions with another wave. The amplitude of the combined waves increases, so the sound is louder. Deconstructive interference combines when compressions of one wave combine with the rare fractions of another wave. The amplitude of the combined wave decreases, so sound is softer. We take a look at these speakers here. You can see that we have constructive interference here and destructive interference here. So right here it would be louder. Right at this spot it would be softer. Okay. Constructive interference happens when compressions from one wave overlap compressions with another wave. The sound is louder because it's combined amplitude. Deconstructive happens when compressions from one wave overlap the rare fractions from another. The sound is softer because it's combining the amplitude is the sound is softer because the combined amplitude is smaller. We also get interference when we talk about breaking the sound barrier. Sound barrier, we have jets that can break the sound barrier. We're going to talk about that here. Interference in the sound barrier. Some jet planes can travel faster than the speed of sound. As the jet travels close to the speed of sound, the sound waves in front of it get closer together. The waves overlap to produce constructive interference. The overlapping waves produce an area of high pressure in front of the jet. This area of high pressure is called the sound barrier. Okay, so what creates the sound barrier? Well, it's the high pressure. The high pressure in front of the airplane creates the sound barrier. When the jet reaches the speed of sound, the waves in front of it pile up on top of each other. This produces a great deal of constructive interference. The amplitude of the wave gets very large. The amplified wave travels out from behind the jet as a shock wave. When the shock wave passes by a person on the ground, the person hears a sonic boom. Okay, a sonic boom. When you hear a sonic boom, that means the jet just broke the sound barrier. Sonic booms can be loud enough to hurt your ears or break windows. The vibrations created by a sonic boom can make the ground shake. The figure on the next page shows how the compressions of the air produces a sonic boom. So if we look at this next page, you can see that the guy is standing here. And once this airplane breaks this barrier, goes fast enough to get in front of the sound, it'll make a sonic boom. The jet is traveling at the speed of sound. The sound waves in front of the jet pile up and interfere constructively. This produces a shock wave that travels out away from the jet. When the shock wave passes the person on the ground, the person hears a sonic boom. All right, the last piece we're going to talk about today is standing waves and resonance. Remember, if we think back to our regular waves, our introductory to waves, a standing wave is a wave that looks like it's standing still because it's got transverse and longitudinal properties. Waves that have the same frequency can interfere to produce a standing wave. A standing wave is a pattern of vibrations that look like the wave is standing still. Standing waves form because the waves travel in both directions in the medium. The waves interfere constructively. They produce an area of high amplitude. Where the waves interfere deconstructively, they produce a low area of low amplitude. You can see this when you pluck a guitar string below. The wave is caused by a fundamental or main frequency of sound the vibrating strings make. If you make the string vibrate at higher frequencies, by making that string tighter, you can see more standing waves. Only some frequency will produce standing waves in a string of a certain length. The frequencies that produce 2 or more standing waves are called resonant frequencies. So if you take a look at this, this would be your guitar string. The string vibrates in only in the only standing wave. The frequency of the sound the string produces is the fundamental frequency. This string is vibrating in 2 standing waves. The frequency of the sound the string produces is 2 times the frequency of the fundamental. This frequency is called the first overtone. So when you double the frequency, you get the first overtone. This string is vibrating to produce the second overtone. This is the frequency is 3 times the fundamental overtone. So you can see here in your thing, this has got 1 wave. Second overtone has 2 waves. Third overtone has 3 waves. 3 little crests here, crest, crest, crest. And the next one, this is the first overtone, has 2 waves, and I think I said this correctly, or maybe incorrectly, but the second overtone has, if you really look at it, it only has 2 waves. This is really only 1 wave because it goes from resting position back to resting position. This has 2 waves, 1, 2. This one down here, the string is vibrating to produce the third overtone as the frequency is 4 times the fundamental frequency. So look at here, it goes trough to crest, 1 wave, trough to crest is 2. So this would be like not even a wave. This would be like a half a wave. This would be 1 wave. This would be 1.5 waves. This would be 1, 2 waves. All right. Now let's talk about resonance. Resonance happens when a vibrating object causes a second object to vibrate. The second object vibrates with a larger amplitude than the first object. Therefore, resonance causes the sound to be amplified. To understand resonance, imagine being pushed on a swing. You swing at a certain frequency, the fundamental frequency of the swing. You always travel from highest to lowest point in the same amount of time. Now imagine that someone continues to push you as you swing. If the person pushes you at the fundamental frequency of the swing, you will swing higher and higher. In other words, the push causes resonance in your swinging. So if we take a look at this, here's you just normally swinging. A person is swinging. We'll just keep going back. Now, if you add somebody else to the equation, you still start swinging, but you're going to go higher. So your amplitude is going to be higher. It's going to be louder. When the swing is pushed, it swings higher and higher. The amplitude of the swing increases because of pushes at the fundamental frequency of the swing. So it's not like they're pushing faster or slower. The fundamental frequency is what it's saying. It's consistent. It's like a metronome. It just goes doot, 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 doot. Resonance in musical instruments. Musical instruments use resonance to make sound. For example, string instruments resonate when they are played. A guitar or violin is an example of a string instrument. When the strings are plucked, they vibrate. The sound waves resonate inside the body of the instrument. This causes the sound to be amplified. That's why there's the hole in the violin or in the guitar. When you blow air through a mouthpiece of a flute, you make the air in the mouthpiece vibrate. These vibrations resonate inside the instrument. The sound of the instrument is amplified. So having that circle, if you ever taken like a little Bluetooth speaker and put it inside like a container, it gets louder because inside it vibrates. Let's take a look at the reading check here. What happens to sound inside a musical instrument due to its resonance? So what happens to it is what? It gets louder. Like when I used to go golfing, I used to have this little Bluetooth speaker, and I put it in my golf cart. I put it in a little cup holder, and it gets louder and louder because it resonates with the sound. It vibrates. It amplifies the sound. All right, guys, this is lesson number 3. We have 1 more lesson on sound and 2 lessons on light, and then that'll do it for the year. So keep on going. We're getting there. All right. Thanks, guys. Bye.